পাচ্ছো আমার কথা?
হ্যাঁ ম্যাম, শুনতে পাচ্ছি।
ঠিক আছে। We'll discuss the transient characteristics of DC and motor and induction motor. Actually, previously this was included in your machine syllabus, but when the syllabus was revised, it is now included in drives. Because when designing the drive system, the transient characteristics are important. Now, about the transient, we will only discuss the starting and braking, not fault or anything. Starting and braking. Now, why starting is important? You have seen that while defining the duty cycle, also there are particular duty cycles where starting time was considered separately if the motor requires high starting torque and starting current, because that affects the system. So what are the effects of starting? What are the effect of starting on power supply, motor and the load? Now, first of all, the excessive voltage during starting, the motor draws a large current, so there will be voltage drop. Normally there will be a voltage drop, but there will be an excessive voltage drop due to the peak starting current. Say for example, the induction motor. It can be started online, but it takes some 6-7 times the full load current for a few very short time period, say 10 or 20 seconds. But that in that time period, there will be a high voltage drop. So that drop affects the other loads connected to the supply. So the excessive voltage drop due to peak starting current may interfere with the supply in such a way that it cannot be tolerated by other equipments or other consumers connected to the same power supply networks. So then, since starting is associated with excessive current, so it is excessive current, that will be higher I square R loss. So if the starting time is longer, maybe due to the high inertia or type of the load it is connected to the shaft, then it is important. The starting current will add to the motor heating by an amount that depends on their RMS values and upon the frequency of starting. So if it is a intermittent duty type load that it is stopped and started frequently, then it affects the temperature rise. So in DC motor, boot commutation is important. Now DC motor, there is a moving contact, the commutator and the brush, and there is, however well the motor is maintained, there will be sparking because it is a moving contact. So during in commutator segments, you know, we have copper segments insulated by thin mica separators. Now there is a voltage that mica separator can withstand. Now if the current increases, there is a possibility of flashover from one commutator to another. So the DC motor boot commutation is important, as DC motor has a certain maximum limit for the current dictated by the commutation process. The equipment connected to the driving motor may impose strict constraints upon the type of accelerating cycle and upon the maximum permissible acceleration. That is, for example, if in a particular system, if some type of load is connected, which has a intermittent duty cycle, very frequently started and during starting takes a high current, so the other loads connected to the system will be highly affected. So the other consumers might object to it. So what happens? Discomfort to, say for example, discomfort to passengers in lifts and trains may set up upper limit to the rate of acceleration. This is related to the acceleration. So for starting period, say for the lift and the escalator, etc., there will be acceleration. So what is the rate of acceleration, that is important, because if it is particularly a locomotive or lift, then we cannot have a very high acceleration, because that will be discomfortable for that passengers will feel discomfort. Will feel discomfort. Now, say for cranes, excavators, and other material handling equipments. So the equipment and the operator has precise control over the load, whether it is light or heavy. So unless the system is designed properly and the operator cannot control it very precisely, it is difficult, because in this case, not only the weight of the material, the type of material it is handling, whether it is fragile or uh, other type of material, that depends on that also. So some consideration must be given during design. So for these machines also, the starting process is very important. Say then next point is that in case of loads which exhibits friction, the motor must develop sufficient torque to overcome it, after which the torque may be reduced. Now, friction is static friction. Say for locomotives, we have electric locomotives. So locomotives, the load curve, the torque, what happens initially, the initial torque requirement when it is started from rest is higher, then it slightly decreases over some speed range, become minimum. Then against because the friction, that is the static friction, decreases, and as the speed increases, dynamic friction increases. So there is a, after a small speed, the vehicle gains a small speed, then the dynamic friction predominates, and it will increase proportional to the friction. So this static friction has to be overcome. Now, static friction, during static friction, as it is starting from rest, static friction, that inertia of the device is also is there. So the driving motor should overcome all these. So that is why for traction motors we require a very large starting torque initially, and that's why series motors were very suitable. Though now we can have induction motor operating for it, but with control, the characteristic what we will get will suit the load torque requirement. That is, we will have a high starting torque. So so for these reasons, the starting, we should know the what is the starting characteristic. So for designing a system, the motor starting and braking characteristics is very important. Now we will discuss starting methods of DC machine and induction machine, which are most widely used. Now, what are the general starting method? First of all, is obviously full load starting. It involves application of the full line voltage to the motor terminals. Now, obviously, DC motor we cannot have it, but induction motor we can have full load starting or DOS starting. Then we can have reduced voltage starting. Now, reduced voltage starting, say for DC motor, when we apply a starter, if you remember a 4-point or 3-point starter, that is basically a reduced voltage starting. That is, we insert a resistance in series with the armature, and the part of the voltage is dropped in that resistance, so a smaller voltage is applied across the armature. Uh, Now, when we go for automatic starter, also the same principle is there. That is, it is not the resistance is not cut off manually, but it is cut off in stage. If we have a power electronic controller, then we can have a step increase of the voltage with frequency, so that we can have a very gradual rise of the voltage. And there also the same that Reason is the same. That is, we are applying a reduced voltage. Similarly, we can have reduced voltage starting for induction motors. Induction motor reduced voltage starting. The simplest one is stator. Simplest are the stator reactor or stator resistance starting. That is, reactor or resistance is inserted in series with the stator winding. So a part of the voltage is dropped. Now, normally we know reactor is inserted because resistance means it will result in losses, larger I square R loss. But there might be some applications where reactance, insertion of reactance may slow down the process, might cause some trouble. So, in that case, resistance starting is preferable. Most common is the auto transformer starting. That is, we apply a reduced voltage through an auto transformer, which can be increased gradually. So we can have a soft starting. Then we can have start delta starting also. This is also possible only if the running connection of the stator winding is delta. Then we can connect the initially in start and then change over to delta. So the starting current is reduced. The third method is increased torque starting. In case of slip ring induction motor, resistance is inserted in the rotor circuit so that we will have the that characteristic is shifted. We can have with the proper value of the resistance, we can have the peak torque at starting. So we will have higher starting torque. Then we have to cut off the resistance, otherwise there will be high losses in the system. Both method is starting by means of smooth variation of voltage and frequency. So, in case of DC motor, motor generator sets, DC motor can be started by varying the voltage smoothly. Both induction and synchronous machines can be started by smooth variation of voltage and frequency. Here, both voltage and frequency has to be varied because if we only vary the voltage, keeping the frequency constant, flux will change, so that will change the characteristic and operation of the motor. So to keep the flux constant, we change the voltage and frequency, that is V by F ratio remains constant. So V by F controller is very widely used for AC motors, both induction and synchronous. First, let us see the shunt motor starting characteristic. Now, we will make some simple assumptions. We are considering shunt motor. Shunt motor, we are saying shunt motor in general in drive. Shunt motor does not mean the field is connected in parallel with the armature directly. Normally, the field is supplied from separate supply. So basically, this applies to both the separately excited motor and if the field is connected in parallel with armature. But normally, separately excited motors are used because then we can control the armature and the field separately. So if the field is from a separate supply, so we can keep the flux constant. So supply voltage V is kept constant. Load torque TL, we are considering deriving the expression for load torque TL constant, and for DC we are considering the inductance of the armature is negligible. In fact, actually the effect of inductance will not be there for DC. So these are the basic equation, that is the voltage is equal to the back EMF plus IR drop. Back EMF, this is C constant proportional to the speed in RPS. That is this is radian per second in omega. So I is equal to V minus C omega by R. Now the torque is equal to C into I, the same constant, if you remember the expressions. So this is the torque developed by the motor. Now the torque developed by the motor that should balance the load torque, plus there will be windage and bearing friction torque, and that is normally very small, so normally neglected. So normal condition, that is normal steady state condition, the motor developed torque is should be equal to the load torque. But when we are considering the transient condition, then we should consider the d omega dt, that the inertia torque, because the inertia torque magnitude is comparable with the load torque. So from here, this, if we replace I from this equation, it will become CV minus C square omega by R is equal to J d omega dt plus TL. So CV minus C square omega equal to, taking R here, JR d omega dt plus RTL. If we divide by C square, so this will be V by C equal to this omega taken here. So this is omega plus JR by C square omega dt plus RTL by C square. Now V by C, from this equation, at no load condition, considering I is very small, if we neglect this, so V by C will be approximately the no load speed. There's a, there will be a positive sign here. This is there is a typing mistake. So this is omega 0 omega plus gr by c square. This is the mechanical time constant Tm d omega dt. It should be plus del omega L. This is del omega L is the change in torque. This quantity, this is a dimension of speed. Speed dropped, this del omega L is a speed change in speed due to load. So TEM is electromechanical time constant. TEM is equal to, you see, approximately that if we define the short circuit current is equal to C omega 0 by R. That is the T short circuit, that is the torque produced by T short circuit current I short circuit is equal to C into I equal to C square omega 0 by R. Replacing this. So from here, R by C square is equal to omega 0 by T short circuit. So TEM, which is JR by C square, can be written as J omega 0 by T short circuit. Now if we plot, this is at omega 0, and this is omega, and this is torque. So this curve is so this is omega 0 plus omega plus this j omega 0 t short circuit. They are just that define the TEM. So TEM is the time a drive with a polar moment of inertia J will take to accelerate without load from standstill up to omega 0 at constant torque equal to that of the short circuit torque T short circuit. It depends on the ratio omega 0 and T short circuit. It with increase in armature circuit resistance, T short circuit will decrease. So the time constant will rise accordingly. TEM is independent of load. It does not depend on load, but it depends on the resistance in the armature circuit. So this is the definition of electromagnetic time constant. That is, it is the time the machine will any drive will take. Drive with polar moment of inertia J will take to accelerate without load to the speed omega zero, no load speed omega zero, when the torque produced by the machine is equal to the short circuit torque. That is how it is defined, the electromagnetic time constant. Now, this was the equation, that is omega 0 is equal to omega plus TEM dw dt plus del omega L. So dw dt plus omega by Tm is equal to omega 0 minus del omega L by Tem. Now, solution of equation of this form will be omega is equal to omega 0 minus del omega L. This is the final speed attainable plus C1 e to the power minus T by Tem. This is the form, this is the exponential equation. Now we have to determine C1. So at T is equal to 0, say omega is equal to omega initial. That is, we are deriving for general, so the omega initial. So omega initial is equal to omega 0 minus del omega L plus C1. So our C1 will be omega initial minus omega 0 minus del omega L. Now omega 0 is a no load speed and minus del omega L is the drop in speed due to load. So this is omega L basically. That basically the speed with that particular load. So this is say omega L. So in case of starting, omega initial is 0. So omega will be omega L minus omega L e to the power minus T by Tem. That is, this is the equation. So in this equation, this omega is equal to omega. This is omega L, and for starting omega initial is 0, so C1 is minus omega L. So it will be omega L minus omega L e to the power minus T by Tem. If we the motor is running at no load, starting at no load, so then omega L will be omega 0. So omega is equal to omega 0 minus omega 0 e to the power minus T by Tem for no load. So this curve will be this one. This is a exponential curve. So no load speed will be higher. With load, the speed will decrease, but both the curve will have the same form. Now, what happens to the current? Now, from the torque equation, Ci is equal to J d omega dt plus TL. So I is equal to J by C d omega dt plus TL by C. Now, TL by C can be written as IL because torque we have taken as C into I. So if load current is IL, then TL by C is equal to IL. So your I is equal to J by C d omega dt plus IL. Now d omega dt we substitute from this equation. If we substitute, it will be J by C, C1, that is this constant, by TEM e to the power minus T by TEM plus IL. Now for T is equal to 0, the I is I initial value of starting current. So I initial is equal to IL minus J by C, C1 TEM. So I initial minus IL is equal to minus J by C C1 TEM, where or minus I initial minus IL CTEM by J is equal to C1. So this value, if we substitute in this equation, then we get I is equal to, this is the expression of I. So in this expression, this C1 value is substituted from here. So I is equal to IL plus I initial minus IL e to the power minus T by TEM. So if motor starts from rest, then I initial is equal to V by R equal to I short circuit. So I is equal to IL plus I short circuit minus IL e to the power minus T by TEM. So this curve will have a form like this, that is the current will be very high at starting, then it will gradually come down to the steady state value. This is the no load curve, so it is showing that the current is almost zero, and this is with load. So this is the speed time curve, and this is current versus time curve for DC motor starting. Now for the induction motor starting, normally induction motor, the transient equation are derived by DQ axis theory, but that I'm not going into that details. DQ axis theory will, if any of you have the machine spare elective, then it is dealt in this those papers. So we will approximate derive the expression from the torque approximate torque expression of induction motor. If you remember the expression that a torque at any slip S of an induction motor can be neglecting the stator resistance is given by 2 T max by ST by S plus S by ST, where ST is the slip at which the maximum torque occurs. So from this expression, if we derive the expression for no load condition, then load torque is zero. So this torque is equal to J d omega dt. Now induction motor speed omega is equal to omega 0 into 1 minus S, where omega 0 is the synchronous speed. So dw dt is equal to minus omega 0 ds dt. So in d omega dt here we replace it. So here T max by st by s plus s by st is equal to minus j omega 0 ds dt. So we have dt is equal to minus j omega 0 by 2 t max st by s plus s by st ds. So this j omega 0 by this t max by j omega 0, that is the electromagnetic time constant. These are the same form of this one, that is this Tm, j omega 0 by t short circuit. Instead of short circuit, we have maximum torque. So j omega 0 by t max, the electromechanical time constant, it represents the time during which a drive with moment of inertia j will take from rest to attain synchronous speed with maximum motor torque t max. Now we will get the starting time by integrating this expression. So t starting is equal to integral of this. So Tm by T, this is integral from S initial to S final. So there is a minus sign. So just limits have been changed. S final to S initial, St by S plus S by St ds. Now if we integrate it, it will be St log S plus S square by 2. So S square by 2 St. The expression, so your for starting S initial is 0, omega that is speed is 0, that sleep is 1, and the final sleep is say S, is italics, S in italics. So putting the values, we will have T starting will be Tm by 2 minus St log S plus 1 by 2 St minus S square St. So minus log S is log 1 by S. So plus 1 minus S square by 2St. There was 2, that 2 is missing here. So say for the final sleep, if we consider it is 5%, then considering S is equal to 0.05, putting the values, starting TO starting will be approximately this is TM by 2 ST log of 1 by 0.05 plus 1 minus 0.05 square plus 2 ST. So this is approximately 1. So 1 by 2 ST, and this is, from here we get 3 ST. So your T starting by TEM will be 3 ST by 2, that is 1.5 ST plus 1 by 4 ST. So this is the expression for starting time by that electromechanical time constant. Now we can see that this expression depends on the value of sleep at which maximum torque occurs. So if we plot ST versus that T starting by TEM, TO starting by TEM, so it varies like this. It, it is minimum at some point, then again it starting increasing. That is that this this is that. So this at this point, this is for, this is motor torque versus ST. So if ST is equal to 0.407, then this motor torque is maximum and the starting time is minimum. That can be derived the value. For this, we can differentiate dst, that is this expression, depend on st. So for the minimum value, we can differentiate this with respect to st. So dst, t starting by tem, will be dst of this expression. So if we differentiate with respect to st and then solve, we will get this is equation will give st value 1 by 6. We are obviously not considering them in negative. So this is 0.407. So for 0.407, we will have the minimum value. Putting 0.407 for T starting by TEM, that minimum value will be this 1.225. Now, if we vary ST and plot, it will vary like this. So this is the minimum point. So now the sleep at which maximum torque occur, that is a design parameter. So that operation will depend on that. So once the machine is designed, what time it will take to start, that will depend on its this is obvious because what is the value of the maximum torque and where the what is the sleep at maximum torque, that will dictate the characteristic of the machine, operating characteristic. So for designing the system, we should know this value. So this is a design parameter. Now next transient portion is the braking. First we will consider the DC machine braking. So for DC machine, the main braking systems which are used are regenerative braking, rheostatic braking, and lagging or reverse current braking. Now regenerative braking implies that the operating motor the motor is operating as a generator and feeding back the power to the supply. And this can have we can only have this that when the machine is still connected to the network. Here the mechanical energy is converted to the energy electrical energy. A part is obviously dissipated as heat, and the rest is supplied back to the system. Now, as the motor should operate as generator for regenerative braking, so that means that motor must be driven at a speed higher than its no load speed. So, in case of say when we discuss the forward in operation with example of the hoisting load, there as the load was active. Active load means when the load torque direction remains same way in whatever be the motion of the direction of motion. So gravity is the active load torque. Whether we are moving upwards or downwards, gravitational force always acts downwards. So if it is an active load, as it is an active load, when we were loading the loaded cage, we have seen that after a particular point, the motor speed of the motor becomes more than the no load speed. Then the motor becomes generator, and the power is fed back to the supply, and it generator means it developed a braking torque, which will constrain the lowering motion. So that is, so regenerative braking is only possible when the load which is the motor is driving can drive the motor above its no load speed. Now rheostatic braking implies operating the motor as a generator so that the energy is distributed as heat in the rheostat connected to the armature. Now actually if we switch off or switch off, then the motor will always come to a stop. The braking only will, what happens, braking will reduce the time for stop. So for rheostatic braking, what is done, the motor is disconnected and connected across our rheostat. So as it is still rotating, so there will be some voltage, and as the circuit is completed, current will flow. So the rotational energy which is stored will dissipate itself as heat. So the motor will stop quickly. Now plugging involves reconnecting the power system so that motor is driven in the opposite direction, so that it will quickly come to a halt. But it is customary that we should disconnect the supply at that point. Otherwise, the motor will accelerate in the opposite direction. Now for the regenerative braking of DC shunt motor, so we can the regenerative braking of DC shunt motor, it is as I told, normal actually when we are talking about shunt motor, this is a separately excited motor, and we know these separately excited motors are always used in hoisting mechanism. It's and it is switched on for when, as I have told, that when it is switched on for lowering the load, The developed torque and the load torque act in unison. That is, we are lowering the load, so the developed torque is downwards, and the load is also downwards because this is a gravitational pull. The load, so that as this acts in unison, the motor will accelerate. With increase in speed, the induced EMF also increases and becomes at a particular point becomes equal to the supply voltage. Then, when the speed supply voltage when the speed equals the no load speed. At this moment, the armature current and thus TM torque becomes zero. Now, downwards motion is sustained due to the gravitational pull on the load. Now, after this point, the speed becomes greater than the no load speed, and the armature current becomes negative. The drive then acts as a generator and feeds power back to the supply. And the torque will act as a braking torque. The motor attains a steady state speed when the braking torque developed is equal to the load torque. So the characteristic is this is the shunt motor characteristic or separately excited motor. This is the normal. This is the armature resistance RA. So this is some normal characteristic. So rheostatic regenerative braking means this will go in this quadrant. Now, if we insert resistance in the armature circuit, so the slopes will change. So the characteristics will be like this. This is the normal one, and this is with resistance. Then rheostatic braking, as I have told that rheostatic braking, the speed is still near lower than the no load speed. The motor is disconnected from the supply and connected across a rheostat. Motor developed a generating torque and intensely brakes itself. Now what happens? We have connected the motor across a resistance, external resistance X, R, E, X. Now the supply voltage is 0. So if you remember the equation, motor equation, that was V supply voltage was equal to back EMF plus I into R. So your back EMF that applied voltage is 0, but back EMF will be there. So back EMF will be equal to minus I into R plus REX. So the current direction changes. The RA is the armature resistance and REX is the external resistance. Now E is a back EMF, can be written as K phi into omega. So that is equal to minus I into RA plus REX. Now again torque is equal to K phi into I. So omega is equal to, you replace I from here, I is equal to T by K phi. So T by K phi square, T into RA plus RES by K phi square. So this is the expression. So this is the circuit. That is initial. This is the, obviously the field supply should be there. Unless the field supply is there, the motor cannot generate. So the field is connected to the supply. The armature is disconnected from the supply, and this switch is connected here across this resistance. So this will be the speed versus torque curve. This is the expression. So the characteristic is a straight line considering torque is constant. So it will depend on the value of the external resistance. So this is the characteristics. The basic equations are CW plus IR is equal to 0. CW is the back EMF plus IR is equal to 0 because voltage is 0. So CI is equal to J d omega dt plus TL. CI is the torque, developed torque is equal to inertia torque plus TL. So replacing this I value, I will be minus C omega by R. So this expression will be minus c square omega by r is equal to j d omega dt plus TL. Here R is equal to total resistance RA plus R external. So j d omega dt plus TL, bring it this side, plus c square omega by R equal to 1. So j d omega dt is equal to minus TL minus c square omega by R. So j r by c square d omega dt is equal to TL r by c square minus omega. If you remember that expression, this is TEM and this is the change in speed minus del omega. So uh, so this expression will be TEM d omega dt minus del omega minus omega. So we can write it as d omega dt TEM divided by TM. This will be omega by TEM equal to, this has been brought on this side, equal to minus del omega by TEM. The solution will be of the form equal to minus del omega L plus C1 e to the power minus T by TEM. So at T equal to 0, omega is equal to omega L. Omega L is equal to minus del omega L plus C1. So C1 is omega L plus del omega L. So your expression of omega will be minus omega del omega L plus omega L plus del omega L e to the power minus T by TEM. If TL is equal to 0, del omega L is equal to 0 and omega is equal to, and the speed, this is no load, so omega will be equal to omega 0 e to the power minus T by TEM. So we gave this curve too, that is for no load when braking without load. And if we have it is braking with load, so this value is minus del omega L is the steady state value. So the curve, the full curve is this. So basically the machine will stop at this point. And the speed versus curve, if we plot, it's a DC shunt motor, speed torque characteristic is drooping. So for the braking condition, the speed torque characteristic this will be the speed torque expression for the braking condition. So basically it was moving at this point. When we brake, it will move from this curve to this curve and follow this line, and it will, theoretically it goes up to this, but actually it will stop here. In case of dynamic braking without load, the speed curve approaches the x-axis as illustrated in curve 2. When dynamic braking occurs with load, the curve approaches the line minus del omega L. In the case of load torque is active, as for example crane, hoist, etc., then it will approach this. That is, if the load torque is capable of driving the motor, active load torque, then only it can approach here, otherwise it will stop here. For passive load torque, braking series and omega is equal to 0 when omega is 0 is reached. Now for the expression Ci is equal to j d omega dt plus TL. So I is equal to j by c d omega dt plus IL, that is TL by c is equal to IL. Now omega is equal to del omega minus del omega L plus C1 minus T by TEM, what we have derived. So d omega dt is minus C1 by TEM e to the power minus T by TEM. So in expression of I, we substitute this. So this will become the expression. So if T is equal to 0, I is equal to minus I initial. So minus I initial is equal to minus J by C1 by TEM plus IL. If I put in T is equal to 0, so minus I initial plus IL is equal to minus J by C1 by TEM. So C1 will be equal to C TEM I initial plus IL divided by J. So I will be putting in this expression, it will be I initial minus I initial plus IL into e to the power minus T by TEM plus IL. Now if the load torque is active, then we get curve 1 as shown in figure C, that is the initial curve. This is the curve 1. It is obtainable when the load torque is active. This is that is the load characteristic, and this is for the current. So corresponding current characteristic will be like this. We'll have this in low active load torque. We will have this curve, and if the load torque is passive, obviously the braking seizure is here. But follow this curve, and this is for no load. If the time taken to brake the motor from omega initial to any speed omega 1 is t, then omega 1 is equal to minus del omega L plus omega initial plus del omega L e to the power minus T by TEM. So omega 1 plus del omega L is equal to omega initial plus del omega L e to the power minus T by TEM. So the ratio omega 1 plus del omega L by omega initial plus del omega L is equal to e to the power minus T by TEM. So T is equal to TEM log of omega initial plus del omega L by omega 1 by del omega L. Sometimes for deriving the system parameters, this time parameters are required. Now, next is a counter current braking or plugging. The circuit is this counter current braking. Here also the field supply to be remains same. We disconnect from this supply and reconnect, so that this armature circuit is reversed. That is, initially when it was connected in this direction, so the circuit will be traced like this. Now when we connect to the on this side, so the circuit will be, the armature current is reversed. Same supply, but we was reverse the armature connection. The polarity is reversed by changing over switch SW. The latter also introduces a resistance RB in the circuit to limit the current. Figure B illustrates the transition from motoring to counter current braking operation. Now this was the normal operating. Now here just we have reversed it. That means it will be in this quadrant. Okay. So in this quadrant, this quadrant curve, that is third quadrant. So the speed cannot change instantaneously. So what happens when the supply is changed from this point? It will move to this curve and will reverse this curve, reverse along this curve. So we have to disconnect the supply at this point if we want to stop the motor. current braking, we have changed the supply direction. So minus V is equal to C omega plus IR, because omega being a mechanical quantity cannot change instantaneously. Omega direction remains same. So minus V by C is equal to omega plus I R by C. Our torque is equal to Ci is equal to G d omega dt plus TL. So I is equal to J by C d omega dt plus TL by C. So V by C is equal to omega. We are replacing this I. We are replacing by this expression. So R by C, J by C d omega dt plus TL by C. So V by C is equal to omega plus JR by C square d omega dt plus T square R by C square. So minus V by C minus omega minus T square R by C square equal to Tm d omega dt. So Tm d omega dt is equal to minus, this is omega 0. This expression is change in speed, so del omega L and minus omega. So this is the equation. So we'll get omega by integrating. So it will give, the result will be omega is equal to, this is the final speed, omega 0 plus del omega L plus C1 e to the power minus T by TEM. So at T is equal to 0, omega is equal to omega initial equal to omega L. So equal speed for load L. So omega L is equal to minus omega 0 plus del omega L plus C1. So C1 is equal to omega L plus omega 0 plus del omega L. So putting this value, this is the expression of omega. So if we draw, we will have this curve. If the motor is running and with an active load torque, that is load torque does not change sign, the motor speed after reversal will exceed omega 0 by the amount del omega L. It will with load, if we are with load with active load torque, then you will follow this curve. This one is the omega 0 in opposite direction, so it will be this. It will follow this curve. If the motor is reversed without load, then omega 0 is equal to omega L. Del omega L is equal to 0 because change in speed due to load, that is 0. So omega is equal to minus omega 0 plus twice e to the power minus T by TEM. This is represented by curve 2. This is represented by this one. That is for no load. If the motor reversal occurs with passive load, after reaching x-axis, it brakes and approaches as an asymptote to steady state speed minus omega ss, that is curve S. So if it is a passive load, then this is the no load speed, and in the opposite direction the speed will be omega 0 minus del omega L. So this is minus. So with a passive load, you follow curve 1 and approach this speed. So this is for passive load. But if it is active load, then it will be no load speed plus del omega L. So it will follow this curve. And this is for no load. And for the current expression, again the same equations are used. That is Ci is equal to J d omega dt plus TL. So I is equal to J by C d omega dt. TL by C is IL. So omega is equal to minus omega 0 plus del omega L plus C1 e to the power minus T by TEM. So from here we get the value of d omega dt, put it in this expression. So t is equal, this is the expression of I. Now t is equal to 0, I is equal to minus I initial. So minus I initial is equal to this. So minus I initial by IL is equal to J by C square by TEM. So this is the value of C1, putting it This will be the expression. So the corresponding current expression will be like this. That is, curve 1 shows current for active load torque. Curve 2 for TL is equal to 0. Curve 2 for TL equal to 0. So it becomes 0. Curve 1 is for active load torque. We'll approach IL in the opposite, in the negative direction. If it was minus IL, initially it will become plus IL. And if it is a passive load, then it will follow this curve. Passive load torque will follow curve 3. Now, this braking and starting involves quite a amount of energy. So, power drawn by the motor from the supply consists of load torque, kinetic energy of rotation, that is Jw d omega dt, and losses of the motor. If we club the fixed losses with the with load, and losses consist of I square R loss and power required for field excitation. So the energy loss with the armature circuit during transient period of operation is important because it influences the power capacity of the for which the motor must be selected, and the size of the requisite resistance to limit the current. So basically, the rotation, the fixed losses can be clubbed together with the load. So that will not change really with load, but what we will change with current is the I square R loss, the variable loss. This is very important because that affects the temperature rise. So separately, that we can derive the energy loss due to that armature circuit losses. So that will be, say, this for starting process, say t starting is the time. So the loss will be 0 to t start I square R dt. Now V equal to E plus IR. So VI equal to EI plus I square R. So I square R is equal to VI minus EI. Now I is equal to T by C. Approximately we consider T is equal to CI. So V into T by C minus E into T by C. So T into V by C minus E by C. Now V by C is the no load speed and E by C is the speed at load. So T is equal to J d omega dt. We are neglecting load torque considering the no load condition. So dt is equal to J d omega dt. So our expression of energy was I square R dt. I square R dt. So I square R is equal to T omega 0 minus omega dt is equal to J d omega by T. So in terms of the speed, it will be omega initial minus omega final into J into omega 0 minus omega into d omega. So you can see inertia is very important. So at starting at no load, omega initial is 0, omega final is omega 0. So del omega starting is equal to J omega 0 square. Now for any other loads, this integral can be calculated for the energy to be dissipated. for the other expression. We will continue in the next class because there are quite a lot of expressions involved. So next class I will take on next Tuesday. Okay.
Okay, ma'am.
I will take on next Tuesday because next Thursday I have a meeting. I will not be able to take class. So Tuesday I will take a class. Okay.